Right guys, this is the third and final section of the gravity topic. It seems quite short, but this is a big idea. It's lots of stuff that you've covered before, all the way through your GCSE, but this is the proper version and I'm almost guaranteed it will hurt your head. So spend some time on this. I've split it into two PowerPoints, but it's a big topic. We are talking about potential. So, Section 3, gravitational potential. We're quite used to it with electric fields and electricity. When we look at it later, you'll see the links. If you can make the full connections, then you're really doing well. So, we're going to look at gravitational potential as an idea, what it means, and it links into this idea of energy. So, gravitational potential has a symbol V, because it's equivalent to electrical potential, potential difference, and things like that. We're going to look at it, but like a circuit, you've covered gravitational potential before when we talked about potential energy. But this is different because, like a field where you're not constrained, you're going to get a much different shape of field, and therefore forces change and so on. So because it's non-linear, everything's very different and you have to do it in a more thorough way. So we're going to start with the definition of what it is. So gravitational potential is equal to work done, okay, or the work done. But that's energy, not potential. That's potential energy. So it's equal to the work done per unit mass. Okay, so it's per kilogram. Rather like force per kilogram gave you field strength, work done per kilogram gives you potential. Okay, and this unit mass, this test mass, is equal to that work done, moving it from wherever the position is, so here in my diagram, out to infinity. And the reason we define everything by infinity is, firstly, it links everything together in physics, but also the idea that at infinity there is no force acting on it. Okay, so wherever you are in space, you are attracted by nearby planets, stars, etc. But here, if you're an infinite distance away, then there is no force. So if we were to roll in along here in our mass, so if we were in a little test mass, a tiny little person on 1 kilogram, as we got closer to the planet, we'd fall faster and faster because we'd be gaining potential energy, because the field would be doing work. Okay, there's a force on us, and because we're moving over a distance, that force distance or force displacement towards the planet would actually give us energy, increase our energy. What it's doing is we'll be losing potential energy as we went along. So what we're doing is effectively falling towards a planet. Now normally we think of potential energy as moving up from the surface, yeah, almost like climbing a ladder away from the surface. But actually, we're climbing up to where there is no energy. So this is equivalent to the ladders, the energy level ladders in an atom. And because of that, we have to link them all together. So this has negative energy. So this is 0, and all of the potential below this point, or closer to the planet from infinity, is negative. Down to, shall we say, the ground state, the ground, where you have no potential energy. Okay, so higher potential energy, higher and higher, it's getting bigger and bigger, but it's getting closer to 0, which means it must be negative to begin with. That's your first big brain tease. So we'll define it as potential, V, is going to be negative because it's pulling towards it, the planet. Big G is in there, and the mass of the planet makes a difference, so you'll fall a lot faster towards a big mass than you will towards a little mass. And again, it fits with radius, but this time it is radius, not radius squared. Okay, so note bene, it has no power there. Okay, or rather power 1. So I've said why. Okay, a bit of detail here. And so, firstly, mistake. We lose height. That should say. I obviously was having a bad day when I did this paragraph because not only have I put the wrong word, I've also misspelled gravity. Gravitational, so you can check that one and correct it to your own delight. Okay, so effectively, because the force is radial around our object, our planet in this case, everything gets pulled inwards towards it. So effectively we can visualize this whole thing as a whole, and this is where we popularly see the diagrams to do with the gravitational potential ideas of Einstein. So this is slightly different. This is a ladder, this is a graph of potential energy, and we'll come to the actual simple version of the graph in a minute, but it has a certain shape of graph, okay, a 1 over r graph, where r is the radius from the centre, and it goes off in all directions. Einstein's was slightly different. His was space-time. His was dimensions rather than energy. But you can think of it in a similar way. It is kind of useful. So, potential is measured in joules per kilogram because it's the amount of energy to lift each kilogram up by a certain amount. So, if this had a potential of minus 5 million joules per kilogram, it would take me 5 million joules to get that kilogram out of here. If it's 2 kilograms, we just multiply it up. So it would be 2 times 5 million, 10 million, etc. Now, if we link it all together from our definition, we'll kind of come full circle back to where we were. So, year 12, and in earlier, of course, we had the gravitational energy at a height above the surface, okay, as the potential equals mgh, okay, which is all well and good as long as that is uniform. The gravitational field strength is uniform with height. And unfortunately it isn't. So that only works for a uniform field. Okay? In a radial field we need a much better way of looking at it, where G is, from our gravitational field strength equation we had before, G m over r squared. Okay? Now if we break that down, again we're slightly cheating here, we should do it in a slightly more thorough way, but we'll come back to that. We can think about this gravitational or potential energy as putting the two parts together. So we've got our mgh, we have mgm over r squared. Now I am missing negative here, but we'll come back to that in a second, times by r. And so what we end up with is, if we want to get a proper equation for correct equation for gravitational potential energy, then what we actually need is, and I'll just tidy up ever so slightly, mm over r. So again, note, it looks like the force equation, but it only has single r, not r squared. So again, note the difference. So there's a similarity. That equation is similar to gravitational field strength. That equation is similar to force, and there is a four-way link between the two. They all do interconnect. Now, as I said here, we have dropped the sign, but actually it does matter. Direction does matter because we're moving away. So I'm just going to, kind of put in brackets there that we do have that. Okay. So direction is important, but it doesn't matter as long as the direction is away from or towards the planet. Now, interestingly, that does mean that if we are on a surface like there, that point, I don't know how well you can see that line, but if we move around that line, that same potential, then what we find is that we don't need to fight against the gravitational field. The gravitational field is also not pulling us in. So actually, we don't need to do any work to move along that level. Okay. Now in the PowerPoint, I use the idea of contours, and effectively it's a similar thing. If you're looking at the paddy field pictures that I've got, to walk along the paddy field is really, really nice and straightforward. If you fall off the paddy field, gravity will pull you down very rapidly. And it takes a lot of hard work to climb up the layers of paddy field to get away from the thing. So again, it's just like crossing contours going up and down hill. Walkers will often follow a contour because it's a nice easy path, much less effort. Now in space, where there's no friction, you just, once you're out and moving at a speed in an orbit, you stay in that orbit. You do not need to have your engines, your rockets on still on anything in orbit. It just goes around at that same height with no added or subtracted energy. So, quite a powerful idea, thinking about where we go from that, but we need to simplify it because, again, these are complicated equations. That one is equivalent to this one. It depends on the shape of the field. We need a more universal law. So, if we turn over to the next page, then we actually get the true version of the equation, which is this gravitational energy, okay, and I'm going to change it to grav now. So gravitational energy is mass times potential, okay, and that's a really, really important equation. Just like gravitational field strength was force per unit mass. Okay, so we can link these ideas together. Energy per mass will give us potential. Very powerful equation, and that is always true no matter what object we're talking about. Now, again, I'm really labouring this because people always get this wrong. When people think about moving objects within a field, what they tend to do is think, how far have I moved it? Okay, that works. That work done idea, force times distance, works fine if the force is constant. But the point with this, the idea of drawing this on a slope, is that there's a much greater force close to a planet, much less as we go out. Okay, so this also indicates the force. The gradient of this indicates the force. The change gives us the potential, but the gradient is forever changing. So the force is forever changing. Which means that when we do the mathematics, if you want to know how much energy to get from A to B, you can't just subtract the distance. You actually need to go fuller into it. So if we want to work done, okay, I'll put the caveat in afterwards, then the work is the change in potential. Okay, that's not genius. Okay, so still conversion of energy gained or energy lost is due to work done either against the gravitational field or by the gravitational field. That will give you the gain or loss. But what we have is our first potential, which will be mv, subtract the second one. Except, of course, I said that wrong, isn't it? You always subtract your initial potential from the second one. So we're going to start with the bigger value, should we say, the second value, subtract the first one. So that, obviously mass has the same difference there, same mass value in both of them. So you can simplify it a little bit to that, but you have to work out the potential at each of those to then subtract them. Don't just fall into the trap of saying, well, I can just subtract the radius. No, you can't, because it's 1 over radius. Okay, it's a different matter completely. So you have to find those values of potential using that, and then subtract them, and then multiply by the little mass that you're moving about afterwards. Okay, so be wary. Do not just use distance moved. I'm going to say displacement. Okay, as it says there is no shortcut. So really, I know I've written it here, but people ignore it. So do not, very, very, very important, do that. So when we're talking about our hole with our planets at the bottom, we're actually talking about a graph. Okay, so if we have that equation and you plot those values for that equation there, then what we'll end up with is this graph here. Okay, so this is a 1 over r graph. It's negative. Okay, so there's our 0 level there. This is negative value, and this slight lie. Oops, I've just looked at the wrong graph. This is our value down here. So again, it's our negative g, gravitational field strength. Excuse me. So it's 1 over r squared. If we work out the area, then that is the gravitational field strength multiplied by distance, and I should say this is the area above the curve, between the 0 line and the curve. So the area under is actually equal to the work done, depending where you go from. So if you wanted to find out how much work to get from here to here, you could work out the area and do that. Obviously, if you have the equation and you want area, well, you can integrate it. I'm not going to do it here, but you can integrate the two values, or the values from there to there after you've integrated it. And what you'll end up with is this second graph. And this one is a lot less steeply curved because this is the 1 over r graph. Okay, so this is potential, this is G. Okay, so that's the shape of our hole that we fall into. Notice it only goes to there. And likewise, that's because the force only goes to there. Why? Because r is the radius of the planet. So, planet or star or whatever, it's the surface. You can't fall further than the surface. Let's say that. So, if you found that tricky, it's easier to think of this in reverse. As I described before, the rate of change, sorry, not the rate, but the change in potential with radius, the gradient, actually will give us work done. Okay, will give us the previous graph, the gravitational field strength. So this is probably easier to think about, this idea of force. Now, if I multiplied this by mass, if I multiplied this graph by the little mass that we're moving, then we'd end up with gravitational potential energy. Okay, and if I found the gradient, it would give me the force. So that's a similar way of thinking about it. So if we take that that gradient there, okay, gradient, as I say, 2 points there, gives field strength, which fairly obviously, but worth stating I think, is not constant. Okay, so it's not a linear graph. And in terms of this whole thinking, we just need to kind of work out what's going on with a lot of these things. We are looking at the value of radius away from the planet. Okay, so don't think too much about the hole. The hole is like a metaphor to describe what's going on. What we actually want is, as it says here, the real potential well. We can think about how these things work and how much energy is needed to move towards and away from things. Okay, but you do have to be careful. You need to make sure that you don't fall into the lazy way of thinking. This field changes shape and changes strength. So when we go back to, let me just link back to my hole here, don't forget that actually it's not about this height up the hole. This is actually a graph of potential, and this is radius. Okay, so radius being radius from the centre of gravity, centre of the gravitational field, centre of mass. Okay, so interesting thing, very awkward. We used to go into a lot more depth, we used to integrate it in various things like that. You don't need that, you need to have a nice clear understanding of what this is. So the best way of looking at that, I think, is to take us into our last section, which we'll butt up with, which is about the idea of escape velocity. So we'll do it all in one step because I think this illustrates nicely what's going on. What we've got here is a fairly typical 1 over r curved. Okay, so it's the potential energy per unit mass. It's an American graph. In other words, it's the potential. Okay, so this is V up here. Here we have our slightly dodgy height, which is going to be something, a little bit subtract. So r subtract r of Earth. Okay, so just to give you an idea, so really 0 should be here. We're starting at the dotted line. That's not a problem. What we've got going on is at different radii from the Earth, we have a different potential. So don't fall into this trap, as I was saying. This is a low Earth orbit, so this is satellites that are going over the poles. Some of them go other directions as well, but pretty low to the surface. That is not the height. Okay, this is a geosynchronous orbit. It is not 6 times further from the planet's surface. Okay, what we're actually looking at is if we're looking at height, we're taking off this axis here. So low Earth orbit is really low. Yeah, geosynchronous is actually pretty damn high. So it's, as we did the calculations before, it's about 36,000 meters. Okay. So, sorry, kilometers. That wouldn't be very high. So yeah, this is our height scale. Okay, this is the important bit to think about. What you're doing is reading off the energy from this. Okay, so don't think of this as height or anything to do with that. That's where you fall into this trap. You want distance horizontally. It is not a distance vertically. So it's not to climb out of the hole, it's climbing sideways from the hole. How much effort takes is upwards. Okay, so think of height as effort rather than distance. So if we kind of break that down a bit, what we can say is basically nice and simple, is if we want to be able to escape, well, the laws of thermodynamics still work, energy is conserved, we need a change in gravitational energy, and that is going to turn into kinetic energy. It's not genius. Okay, so that's our crucial law about it all. We're still looking at change of energy into another type of energy. How we need to do work, we need forces to make it happen. So the bit in here is going to come from the work done. Okay, and that work done will be by the rocket engines. A Saturn V rocket that we've got there. So that goes to quite simply gravitational potential energy equation that we've just had. So Gm over R, but it's potential energy because we want the energy now. So for every kilogram, that's how much we need. But if it's more, then we need to multiply it, scale it up by m. We know that that is going to turn into kinetic energy of that mass. So again, actually, this is why the idea of potential is so useful. It's going to be the same whatever. So it doesn't matter how massive the object you're moving is, the velocity it needs to reach to escape will be the same. Okay? Now, just going to give you a warning here. We don't necessarily mean escape. We want actually this change happening, or this change will happen, sorry, at any change in radius. So to get from a low Earth orbit to a high Earth orbit needs a certain amount of energy. It needs less energy than it takes to get from the surface. Okay, so it all depends on how far you want to get away from the hole. If you want to go to infinity, then you don't need an infinite amount of energy, you need that much energy. Okay, and to give you the idea for Earth, if you look on this scale, you could take a bit of an educated guess, put the mass of the Earth into the equation, that's actually 62.5 megajoules for every kilogram that you raise up. Okay, so it's not infinite amount of energy, again, that's infinite distance away, the actual energy is the scale up the fiddle. So, if we wanted to rearrange that, make that a little bit easier, then v squared equals 2gm over r. So the velocity you need to escape depends on the mass of the planet that you're escaping from and the radius of it. So links in with density, you can quite often work that out. So we're going to put all the things together. So it depends on m, r, and therefore density. Now, just make clear these are notes, so I'm just using this kind of hint in here. If you're doing write-ups in the exam, don't use shortcuts. So it depends on m, depends on r, depends on the mass of the planet. Okay, so that's the planet you are escaping, or moon, whatever it is. Oops, sorry, plant. To escape from the planet. But it's going to depend on the density of the planet. The Earth and the Moon are fairly similar, but it does mean, because of different radiuses, that you therefore have different masses, and you'll actually end up with a different escape speed, which is good. It's harder to escape the Earth than it is the Moon. Is there a way of imagining that? Is there a way of shortening that? Well, yeah, again, have a look at the PowerPoint. because it gives you some explanations. It gives you a whole series of dips for different planets as we get out. The moon, because it's not as massive, and this is where that wonderful video comes in for American teacher showing his class with a giant rubber sheet. If you had a smaller mass, it wouldn't dent it as much, therefore it's actually easy, it won't dip as much, therefore it's easier to get out. So it has a lower need for energy to escape, therefore you need less fuel, therefore you get less velocity needed to get away from the orbit, okay, to get away from the surface. So taking off from the moon, even though it's about the same density of the Earth, because of its smaller radius, r cubed for a sphere, mass is much, much smaller, so therefore you're going to find that your escape velocity from the moon is quite low. But for Earth, okay, just be a little bit careful here. We'll add on a little bit of detail, because there is one other little caveat. No, let's do the Earth first. So for the Earth, again, if you put the mass of the Earth in, what you'll find is V is basically 11.2 to 3 significant figures kilometers per second. Okay, so that's from our calculations using the mass of the Earth. Does this reach that speed? Yes, but it does it progressively, hence the stages in the rocket. If you tried shooting or throwing something at that speed, you could achieve it potentially with a fast enough gun, but the impulse, the size of the force and the rate of change of momentum would mean that anything that was squashable would get squashed. If it was a human being fired from a gun, to get to that speed, you'd end up with a flat pancake of a person. They'd actually be killed instantly. For again, anyone who's seen Martian, the idea of the size of the forces would explain why they tried the initial rocket to rescue them. It flew off course because liquefaction. So they put some food up that was fairly solid, but because of the forces, it actually turned that, and the vibrations on it caused that to liquefy, and that caused to then flow around and the rocket tipped off, etc, etc. So yeah, forces need to be kept under control, therefore we use progression to get up to this speed rather than doing it in one. So it might be slow, effectively using that idea of Newton's gun to get you higher and higher and higher, which is also why we have parking orbits. For example, the ISS is being used as the basis for missions for future, because you don't need much energy to get up the gentle slope, shall we say, from there. So, one crucial thing that matters, and again comes into where we launch these from, European rockets either launch from Russia, as are America now, because they're starting to use these things. So Americans are starting to use Russian territory, Siberia and so on. Northern part of Southern America, okay, so Venezuela and all that kind of area. Perhaps not Venezuela, but next to it in Guyana, French Guyana, for example, and Florida. Why? Because they are actually nearer the equator. The Earth is spinning at the equator. So this calculation is actually just based on us, on a stationary planet, getting up out of here to get to wherever. Okay? So notice this doesn't depend on where the radius is from, it's just getting us up this gradient. That's where this calculation comes in. Now, if we are spinning, then you already have some kinetic energy, therefore the increase doesn't need to be as big. To get that change in potential, we already have some kinetic energy, we need to do a little bit more. So this is getting us up to the idea of, and I'll just say here, where r is the radius, I should add, hang on, to leave the surface. However, where r is the radius of the, and I'll put in brackets, in speech marks here, the orbit of the mass. Okay, so the mass could be on the surface of the planet, but if it's here, then it's that radius that matters. Okay, if it's here to escape from here, then it's that radius that goes into the equation. So whichever radius is appropriate goes into that equation. not, put in brackets, not including the kinetic energy that it already has. Okay, the fact that it's moving on the ground. So here we go. We've got these basic things, and of course there is another aspect that this is assuming 100% conversion. Nothing's 100% efficient, so you're going to need more energy than that to put into it. So you won't get this in the exam, but just to make the picture fuller, if we want to actually start doing rocket science and getting people into space and that kind of thing, then we need to think about how much work needs to be done. And to do that, we need the total energy. So total energy in this case is going to be, I'll just put a sigma there, it's going to be half mv squared plus negative gm m over r. Okay. Now from that we can simplify, we can use things above and so on, but actually what we're after is this ideal work. So if you had work to change orbit, let's put into change orbit, then the work is going to equal your second version, so half mv2 squared minus g m r2, okay, subtract half mv squared for the first velocity, subtract, or then again we can do the maths on that in a clearer way, but the first radius. Okay, so it looks complicated with stuff like that, but just keep in your head, it's just finding out the total energy you've got before, total energy afterwards, and the difference is the work done. Okay, so I don't think you get anything like that. That's even nasty for AQA. However, for this idea of escape velocity, I think drives home this idea of what this graph actually represents. So that's the value of energy that you're after for every kilogram, and that's how far you're moving away from the planet itself. Okay, so be wary getting trapped into the superficial, looking at a bit of a curve in space and going, aha, that's the idea. It's a bit more complicated than that, because that's a three-dimensional graph, okay, or a two-dimensional surface representing 3 dimensions. Okay, that takes us to the end of the chapter. There is an awful lot of practice you need to do. As I said before, it's a dead common question, gravitational fields. If you get the forces stuff, I think it's easier. But if you've got some visualization in your head of the graph and how that represents, and also things like no change in energy, okay, of something going in orbit, then that makes it easier as well. So beware on things like that for multiple choice questions, but for the others, if it's about potential, just keep it nice and simple, and the important bit is lost is that bit there where you need to find the 2 potentials and subtract them. Okay, there's going to be a question. Practice, practice, practice. Use my model answers and then do the shed loads of practice as well. Okay.